So in the last lecture, we started talking about sampling, right? And in sampling, we talked about two things. One, how you can use samples generated from a distribution to calculate statistical quantities, which may include the mean, the variance, the PDF, and so on and so forth. And in that context, we talked about the law of large number, which is the foundational element for sampling method. And then we said that, okay, we can represent statistical quantities using sampling, but who is going to give us those samples? And in that context, we started talking about the inverse sampling. So in a nutshell, this slide basically reviews everything we talked about in our last lecture. We talked about how you can represent things using sampling or samples, and then we talked about at the bottom left the inverse CDF method, where the idea is you draw samples from a uniform and then use the inverse CDF, and that will give you sample from the target distribution. And we did prove that yes, if you sample like this, you get samples from the distribution of interest, which is pi x. But what was the problem? The problem is that this inverse CDF approach only works if we can calculate the inverse CDF. If we can calculate fx inverse, only then we can use this inverse CDF approach, right? So the challenge is that inverse CDF only works if fx inverse can be computed, right? Only if you can compute the fx inverse, under that circumstances only you can use the inverse sampling or inverse CDF approach, correct? Now, why is this a problem? This is a problem. So for us, this is a problem because we do not know the target distribution, we do not know the posterior, because we will not have access to the posterior. We will not have access to the posterior, which is probability of theta given the data. And remind me, why is it that we will not have access to the posterior? What is the bottleneck here? Why is it that we will not have access to this posterior? What is the problem with computing this? What is the problem? What? Estimating the certain point. Why can't we calculate probability of theta given d? It has nothing to do with points. How do you calculate probability of theta given d? How do we calculate this posterior? Prior and likelihood and probability evidence. Now, out of these three, which is, do we have everything? What is it that we don't have? Evidence. Why we don't have evidence? It's a high dimensional integral. Last class we did it. So why don't we have this probability of theta given d? Because we don't have evidence. So we do not have access to this probability of theta given d, because to compute it we have to use the Bayes law, and according to the Bayes law, in the denominator there is the evidence, and the evidence is not known to us. The evidence cannot be known to us, because if it is known to us, then we do not need sampling. We are talking about sampling because we cannot calculate the evidence. Okay? So that is the bottleneck.
So is it also not because in the class we have said we don't know the distribution after after the product of likelihood and prior, because
What is
we were using conjugate prior because
wrong?
so if that
Wrong, you have misunderstood. So let me clarify here. This is important. Why were you using conjugate prior? Because then probability of D can be calculated.
okay, so but we didn't discuss it earlier.
We did discuss it in the sense that I said that once you do the likelihood times prior, we are getting the same kind of form. And because we are getting the same kind of form, there was no need to calculate probability of D. So the problem is with probability of D. If you get some different form, for example, if I get the known form, think about the coin tossing example. What is the form we are getting in the posterior portion? What is the form we are getting? Beta. Because the form was beta, what is the normalizing constant for beta? Beta function. So we were calculating that because we knew that because my form is of beta distribution, my normalizing constant is a beta function. Now assume you get a form which is something unusual. What is the normalizing constant? You have to find it. You have to integrate it, and you cannot integrate it. The problem always is in the denominator. With conjugate prior, you get the same form. So since you get the same form, the denominator is automatically known. It's a beta function. Beta a plus n1, comma b plus n0. Beta function. So that is known to us. Gauss inverse gamma, we get the form of Gauss and inverse gamma. For Gauss, we know it is 1 by square root of 2 pi sigma square, let's say it's univariate. And for inverse gamma, we know it has some gamma distribution. So those things become known to us when we use conjugate prior. It's not that we don't need to calculate it, we have to calculate it. And the reason we use conjugate prior because that will make our life easy and computing probability of D becomes trivial. Clear? But now when you are using some unusual prior, then that is not the case. Then you do not know what is probability of D and you have to integrate. And that becomes the problem because you cannot integrate. Clear? What is the issue? Okay. So for this problem, for us this is a problem because we will not have access to the posterior. Okay. In other words, posterior probability of theta given D is only known up to a proportionality constant. This means you know the unnormalized distribution, because you can always do prior times likelihood. That was never the problem because there is no integration. You just have to do product. You can always do the product. So you can compute the unnormalized distribution, but you will not be able to compute the normalized distribution. And because you cannot calculate the normalized distribution, how can you even hope to calculate the CDF of that and the inverse CDF of that? Because how do you calculate CDF? You integrate the PDF. The PDF is not known what to integrate. And if you don't know the CDF, we are not even talking about inverse CDF. Correct? There is no FX inverse. Which means, as I said at the end of the last lecture, that this thing, the inverse CDF approach, cannot be used in our case mostly. Okay? So inverse CDF is not applicable in Bayesian machine learning because you will never know the distribution from which you want to sample completely. Clear? So for us, this is a problem because we will not have access to the posterior. So therefore, we need alternative approach, right? So therefore, we will need alternative approach, right? So that is the motivation, that why we need to talk about other sampling methods, why not only inverse CDF, that was very simple two-line algorithm, why do we even care about anything else? So we care because that cannot be applied directly. That is the only reason we care. Okay. So now, before we start talking about, let us define some terminologies. So some terminologies we need to define. Um, we need to define some terminology. Okay. So first of all, and we need to define or discuss some strategy. Okay. We need to define some terminology and some strategy. Okay. So let's write terminologies and strategy. Actually, terminology and this and strategy. Okay. So now let us think to strategize something, to form a strategy, you first need to be aware of what are the tools, what are the weapons that are available to you. I mean, in a war, if you have to make some strategy, you first have to know, right? That what are the weapons, what is the manpower, what are the things available to you. So if we have to make some strategy to attack this problem, we need to first be aware of what are the tools available to us, right? So what are the tools that are available to us? Let's say. So the tools available to us are, see, first up, so can you tell me, what do you think are the tools available to us? First of all, what we do not have? We do not have the target distribution, or we do not have the posterior in a closed form. We do not know probability of theta given d. But what do we know? We know likelihood and prior, which means we know the unnormalized distribution, right? So the first tool available to us is the unnormalized distribution, right? So that means somehow I have to use this because this is the closest thing to the normalized distribution that is available to us, because this is the closest thing available. So unnormalized distribution, okay, and this is basically, you can write it as P star theta given d, which is equal to P theta multiplied by P of data given theta. Okay. P star means, the star here denotes that it is unnormalized. Okay. We were just doing, because otherwise it should have been a proportional sign should have been there. So I am not writing the proportional sign, that means that this is unnormalized. I am just taking the numerator of the base law. The denominator I am ignoring. Clear? What else do we have? We have a strategy for sampling from any distribution, given I know the distribution and its CDF and its inverse CDF. And that is what the inverse CDF approach basically that we discussed in our last lecture. The second tool we have is that we have already seen how to sample from, we have already seen how to sample from some distribution from a distribution with known PDF, CDF and inverse CDF, right? If these three things are given to us, at least the last thing is given to us, the inverse area, we know how to sample, right? So these are anything else available to us? I don't think anything else is available to us. These are the only thing that are available to us. So now with these tools, we need to strategize and come up with a strategy to sample from the unnormalized distribution, right? Now there can be different strategy. One potential strategy can be that maybe we can sample from some distribution from which we can sample. So some distribution which is not the actual distribution, but some easier distribution from where we can sample. We will sample from there and somehow modify those samples so that it matches the target distribution, right? And somehow modify it so that it matches the target distribution, right? We can think about that. So with this setup, let's say our strategy is sample from some known distribution. And when I say known distribution, it means that you can sample it using the tool number 2, that is the inverse EDF approach, right? So sample from some known distribution and use some trick such that the samples generated resembles either resembles or are is from samples generated are from resembles samples from the original distribution of interest. Okay. The strategy is first select some distribution from which you can sample. You will generate samples and then somehow modify those samples so that the modified version of the samples are from the actual distribution from which you wanted to sample. Is the strategy clear? Now, if the strategy is clear, can you tell me how many distributions do we have now with this setup? If the strategy is clear, how many? 2. What are those 2? 1, from which I want to sample, and that is only known to me in a unnormalized or up to a proportionality constant, right? So that is one distribution that is available to us. The second distribution is the one which I will select, from which I can sample, from which sampling is possible, and so on and so forth. Clear? So that means we have now arrived at 2 distributions. One is the original distribution, the other is the easy to sample distribution, right? And now the terminologies come, what will we call these 2 distributions, so that we don't confuse. So now come the strategy, the terminologies. So, and there are 2 terminologies actually. The first one is known as the target distribution, and this I already introduced last time, but I will write it now for completeness. So target distribution means this is the distribution from which we want to sample. This is the original distribution. This is our posterior. Okay. So target distribution means this is the distribution from which we want to sample, right? This is the distribution from which we want to sample. Okay. Now, what are the properties of these distributions? The number one property is that this is only known up to a proportionality constant. So, this distribution is not completely known to us. So note that target distribution is only known up to a proportionality constant. Okay. The target distribution is only known up to a proportionality constant because we cannot calculate the evidence probability of D. And as a result, we can only do is P star, which is P star theta given D. That's the only thing that is available to us. Okay. And we will denote this as, we will denote this as pi star x. So theta is actually what we are interested in, but because we are talking about sampling now, so we have to remember that this sampling may not be only about sampling the posterior. It can be used for sampling many things. This was developed in statistics and not in machine learning. And in statistics, they were not even probably thinking of computing the posterior. It might be many things. So to generalize, we will call it a target distribution. And we will assume that the target distribution is only known to us up to a proportionality constant. And we will denote it as pi star. Star again denotes that it is unnormalized. If it was normalized, I would have written pi. Okay, so pi for us from now onwards for the sampling part will represent target distribution. Okay. Now there is another distribution, right? And that is a distribution that we select. That is a distribution from which it is easy to sample. So that is a distribution, since we select, we can also say that that is a distribution we propose to sample from. And that's why that distribution is called proposal distribution. So the second distribution is known as the proposal distribution. Okay. And this is basically the distribution from which we want to sample. We sample, not we don't want to sample from it, but this is the one from which we can sample, and this is the distribution that we use to sample. Okay. So this is the distribution from which we sample. Okay. This is the distribution from which we sample. So there is some problem with the screen. Okay, so thank you. So this is the distribution from which we sample or we can sample. Okay. So this is a distribution that we choose. Okay. So this is selected by us, and we will denote it as, QX. Okay. So from here onwards, during the sampling discussion on sampling methods, QX, wherever you see it, it will mean that it's a proposal distribution. It's a distribution that you or I or we have selected, and it's a distribution which is easy to sample from. Okay. Any questions till now? Clear, right? We have done nothing. We have just defined two terminologies and kind of formalized a strategy which is in a vague manner. We will make it more concrete soon. Okay. Okay. So now this strategy that we talked about, right, is a generic strategy. And there are many algorithms that can use this strategy. One such algorithm is the rejection sampling. Okay. So one popular algorithm that uses the strategy discussed before is one popular algorithm that uses the strategy discussed before is the rejection sampling. Rejection sampling. Okay. It is also known as accept reject algorithm. This is also known as the accept reject algorithm, and they are synonymous. Okay. So this is also known as the accept reject algorithm. Okay. Both are same thing, just two names, because ultimately you cannot only reject, you have to also accept. So same thing. Okay. So this is also known as the accept reject algorithm. Now if I go back, so in the strategy there was a sum, right, that I wrote in capital and put inside the inverted comma. So that sum was a sum trick, right? Remember that. So the name generally represents the trick. So I said I will use some trick. Now what is the trick for rejection sampling? To reject samples or to accept certain, reject some certain, so that the distributions, the samples starts looking from this samples that are drawn from pi of x. So the trick, that sum that I wrote inside inverted comma, will change from algorithm to algorithm. In rejection sampling or accept reject algorithm, that sum represents that you will either accept or reject. Okay. So that is the idea. So high level idea is that in rejection sampling, we sample from, in rejection sampling, we sample from qx, and then accept / reject samples such that the remaining samples, so let's write only reject, so reject samples such that the remaining samples are from pi of x. Okay. We do accept also, but we reject samples such that whatever we are not rejecting is from pi of x. Pi of x is my target distribution, which is not known to me. So I will only know pi star, but I have to sample from pi. The relation between pi star and pi is that pi star is the unnormalized version of pi. Okay. So I will not even know pi, but I have to sample from pi. The only thing I will know is pi star, and I can sample from q. So now Naturally, the question comes how to reject, because I now will need a algorithm or a strategy to reject such that the sample, like if you reject arbitrarily, will the samples look like samples from pi x? No. There has to be some strategy involved that will ensure that whatever samples you are retaining or whatever sampling is passing through the filter is now sample from the target distribution. Okay. So now let us talk about the algorithm, but we will not talk about the algorithm. We will first talk about two things. First of all, can any distribution be a proposal distribution? Because I said that Qx is something we will decide. But can I decide just any Qx, or does it need to satisfy certain criteria? So first thing we'll talk about that. What is a good Qx? Second thing that we will talk about is, now once we decide on good Qx, we have to now decide or understand or come up with an algorithm that will allow us to reject in a strategic way such that the remaining samples are from pi x. So then we'll talk about that. So first we'll talk about, can any distribution be used as a proposal? The answer to this is obviously no. Okay, there has to be, for everything there has to be some criteria, but the criteria is very lenient. It's not a very strict criteria, and many of the Q you will see many of the well-known distribution will satisfy this criteria. Okay, apart from some, many of them will satisfy this criteria. Okay, so then what is the criteria for Qx? Criteria for selecting Qx. Okay, the criteria is very simple. Your Qx should supersede your target distribution. That is the only criteria, that your Qx should supersede the target. And you only know pi star, so I am writing pi star, but it can also be pi. Okay. What does it even mean? So let us try to write it down mathematically. What does it mean? It means that mathematically you can define it like a number x by Qx less than infinite. Okay. So SUP means supremum. That means out of the all possible the ratio, the maximum ratio. Okay, that's what M is. So basically X can change. X are samples, so X can change. Pi star and Q are known to you. So you can evaluate pi star and Q at a given X, and you can evaluate it for all X's possible, theoretically. So you will get the number of X you take, that number of M you will, that number of ratio you will get. And then the idea is that M is equal to the maximum of that ratio. Okay. So that SUP means supremum, supreme. So out of a set, the maximum value. That's known as a supremum. But there is one more criteria. It should be less than infinite. So that means it should be finite. What does it mean? It basically means two things. First is that for any X for which pi star is greater than 0, Q should also be greater than 0. Because if Q is equal to 0, Q cannot be less than 0 from the definition of PDF. So if Q is equal to 0, then that will become undefined, infinite. Okay. So this fundamentally means two things. This fundamentally means if pi of x is pi star of x, sorry, is greater than 0, this should automatically imply that q of x is greater than 0. Okay. It should not happen that there is a x for which your pi has a finite probability or finite frequency, but your q does not have any finite probability. Now, do you see any reason behind this? Why is it needed? It's very intuitive. You should be able to think. Why do you think this condition is needed? So, what does a finite pi star means? That there is a finite probability that a x can come from there. So, a sample is possible as long as pi of x star is greater than 0. Correct? That's what it means. But where are you getting the samples from? Q of x. Now, if it happens that qx is equal to 0 at that point, that means that sample you can never get. This basically ensures that wherever pi star exists, q should also exist. So that you, at least in theory, have the chance of getting samples from throughout pi star. Otherwise, it will not be able to sample from every positions of pi star. So that is the fundamental intuition behind this thing. There is another thing, which is the tail probability. Tail means where the probability goes to 0 or very near to 0. So in the tail region, tail of qx should be thicker than the tail of pi star x. Tail of qx should be thicker compared to pi of x or pi star of x. Okay. This again means that even in areas where there is very low probability of pi star x, even in that area you should be able to sample. So it should not happen that there are positions where you cannot sample at all. So fundamentally, whenever you are trying to select a proposal distribution, the proposal distribution should have the capability of sample or generate sample from any place where pi star can potentially exist. So for example, if you want to sample, if your pi star is Gaussian, then what range x can take? Minus infinite to infinite. So then your proposal cannot be a uniform, because uniform is from A to B. If you want to sample from Gaussian using rejection sampling, just as an example, you will not do that, but let's say you want to, then your proposal cannot be an uniform, because uniform is from A to B. It does not go to from minus infinite to infinite. It can neither be a beta. T can be there, but so it has to be some distribution which varies from minus infinite to plus infinite. If you want to sample from a uniform, let's say, but then you can use Gaussian, then it's fine, because Gaussian goes from minus infinite to infinite. That also means that Gaussian is a very good proposal distribution, because Gaussian automatically will satisfy both this criteria. It goes from minus infinite to infinite, so it always satisfies, and it anyways have a thick tail. It does not have a flat tail. So that is also satisfied. So Gaussian is a very good proposal which automatically satisfies this. How do you compare? Just looking at it. You can look into it. You can compute the probability, calculate the CDF of that certain portion. If it is a flatter, then the probability will be less. That's all. Okay. So practically, you will basically, most of the time you will realize you will use Gaussian as your proposal, because that satisfies this criteria automatically. Okay. Clear? The condition for selecting proposal is clear. So now let us go and try to understand how to sample. First graphically, and from the graphical the understanding that we develop from the graphical representation, we will try to formulate the algorithm. And then we will try to mathematically see whether that algorithm holds or not. So we will start with graphical representation. From there we'll try to formulate the algorithm, and then we'll mathematically try to prove that okay, this does work, like we did last time. The graphical one we did not do, but the other two we did. Okay. Okay. So now, suppose I have a target distribution, a distribution from which I want to sample. Let's say my target distribution this is my target distribution. Potential it can be, right? Right? This is my target distribution. Obviously, you can understand this is a distribution from which you cannot sample. The way I have drawn it, it's pretty obvious, okay, that you cannot sample from this distribution. This is my, as I said, I will call it my, this is my pi star x or pi x, okay. Let's call it pi star x because that's what we will know. And you can plot pi star x also, does not matter. What will happen is that it will just get scaled. When if you draw pi x and pi star x, it's just a scaling factor that will come everywhere, right? Because there is a constant that is missing. Okay. So now, suppose I take 2 points on this x axis. So let's say I take 1 point here and I will call it x1, and I take 1 point somewhere here, I will call it x2. What can you say about x1 and x2 by looking at this distribution? Can you say something by looking at this distribution? Or is it that you cannot say anything? Just looking at the figure. Correct? That is the one. You can directly say that x2 is more probable than x1 because the frequency is higher. Right? So from here you can say that. Remember this, we will use this later. Okay? But you know that from here x2 is more probable than x1. Okay? So we will need this in a short while. So now, what is our strategy? We will have to define a proposal. So now in this case, I can see that it goes to 0 somewhere, right? So I will take an uniform because that's easy to explain in the range which should be broader than this one. So let's say my proposal is somewhere here it is starting. This is my proposal density, proposal distribution, and this I will call as Q of x, right? I have not done anything difficult, right? It's very simple. I've just defined 2-3 things. So now I had defined one quantity, but I never used it. I just said that m is equal to supremum of pi star x by qx. Now that comes into picture. So what I will do is, and why am I doing it, I will tell later. So what I will do next is I will create an envelope. An envelope that should, the target distribution should be inside that envelope. So, and I want to create an envelope by modifying the proposal density. Okay. So what I want to do is, step 1, modify qx to create an envelope that encompasses the target. Okay. Any idea how will you create that envelope? Any idea how will I create that? How can I create that envelope? Multiplying m. What was m again? Remind me. Supremum of the ratio of pi star and q. At which point it will be maximum? At the middle point that you say, right? And when you multiply by that factor, what will happen? So that point it will be a tangent, and everywhere else it will supersede. Or so if you create an envelope, uh, so this will increase. Okay, same with this. And this should be a tangent here. This is now my envelope. And this envelope is equal to m times q of x, where m I have already defined here. Remember that m is the supremum. So basically, naturally, what will happen is wherever the ratio is maximum, it will take that value. And when you multiply by that ratio, at that point, q and q will cancel out, and you will get p, because m and m will cancel out, and you will end up getting the pi star, not p, pi star. Okay, and that is at this highest point. Now remember, this is not necessary that the envelope has to be like this. This is the minimum requirement. You can increase m also. So it can also be greater than this. Okay, but this is the minimum where it has to be. Now, why is this envelope is needed? We'll come to that in a while. But for now, let's say that we create an envelope. Okay. Now, as I said earlier, right? Out of x1 and x2, if I sample from qx, which one is more probable? If I sample from qx, same, uniform. But if those samples are supposed to be from pi star, then which one should be more probable? X2. So that means this we have to somehow reject, so that although we are sampling x1 and x2 with equal probability, after rejection, x2 should become more probable than x1. Right? Very broadly speaking, that is something we have to ensure. Now, how much more probable and all those things also needs to be ensured, but we will come to that. So, I will repeat this. When I am sampling from qx, x1 and x2 are equally probable. Uniform, everything is equally probable. Right? But now, if I look into pi star of x, then obviously x2 is more probable than x1. So that means after sampling from the uniform, I should reject in such a way so that x2 become more probable than x1. And not only that, that probability should be a function of this amplitude that we are seeing. Clear? And that is why we need this envelope, because we will use it to ensure this. Okay, and let me show you how. So suppose I have this x1 and x2 I said earlier. So at this x1, I will only take x1, and let's draw this line, vertical line. So what is this point? What is the value of this point? Pi star of x1. Simple. Pi star of x1. What is this point? MQ x1. MQ x1. Okay. So one is pi star of x1. The other one is MQ x1. So now let us try to see what we can do. So the idea is that if I sample x1 100 times, how many times do you think it should be accepted? The number of times out of, if I sample x1 or if I get x1 100 times, do you think every time it should be accepted? No. But the number of times it should be accepted is kind of a function of this pi star x1. You agree to that? That the number of times it has to be accepted has to be some function of pi star x1. Because that's the PDF point. That's the frequency in some sense, right? So how to find out that pi star x1 and how to ensure that the sample x1 in this case is getting accepted according to that number. How to do that? So one simple strategy is as follows. You consider this portion a uniform variable in this axis. So consider this vertical axis to be your axis now. So rotate it and assume that you are generating uniform sampling along those. So basically you are taking this. So rotate the orange line and consider consider that we sample from uniform distribution on that line. Okay. So I will repeat it because it is little tricky. So my line was like this, right? Look at this pen, the line was like this. What I will do is I will rotate it like this. Okay. And now I am saying that I will generate uniform samples here on this line. Okay. So now if I generate uniform samples on this line, and let's say I generate 100 samples on this line, how many of those samples do you think will be below pi star x1 out of 100 samples? I have generated samples in this and uniform samples. How many samples do you think will be below that? Let me put the question in a simpler manner. Consider a uniform distribution in 0 to 1. Okay. How many samples will be below 0.4 out of 100? 40. Because it's uniform, so you just multiply it, you will get it. If it is from 0 to 10, how many samples will be less than 3? 30. Out of 100, I am saying again. So that means if I draw n samples from this uniform distribution, out of those, n times pi star x1 samples should be less than pi star x1. And the remaining should be greater than that. That is the property of uniform distribution because every sample is equally likely. Okay. So this means that what you are doing is that you have this line now, which is the rotated line, and on this you have a uniform distribution. So this is straight, actually uniform. Okay. Now tell me what is this point equal to? What is the axis from here? You can say what is that point equal to? This point. This point is equal to what value? No, we are going in y axis, 0. x1 in x axis, in y axis it is 0. And what is the other point? mqx1, because mqx1 is the y axis. So then what is what are you sampling from? So if you are sampling u, that is coming from uniform distribution, I said, but what is the a and b? What is the lower limit of this and what is the upper limit of this? 0 and mqx1, x1, right? And as I said, if I draw n number of samples, okay, so okay, let me draw this one also. Let's say this was my pi star x1, right? The other magenta point that you see. Okay. So now see if it makes sense or not. If we generate n samples from u 0, MQX1, then how many samples will be below this range? N multiplied by pi star x1 divided by MQX1 proportion, right? Should be this many samples should be in the let's say hashed area, in this area. Okay, area, or rather actually more in this area, to be more specific, right? On this, make sense? Correct? This many samples will be below, less than pi star x1. Other samples will be greater than that. Any doubt? So now, see what will happen. If I use this strategy, now compare x1 and x2. In x2, what will happen? How many samples do you think will be accepted out of 100 at x2? All, right? If I take x3, one x3 between x1 and x2, some samples will be accepted, but that will be more than number of samples accepted for x1. And this acceptance is now following that curve. So that means if I reject or accept, whatever you call it, following this strategy, then my samples that will be retained will follow the pi star x1. So that means if I have to write the algorithm, how will it look? So based on the discussion, see what we can do. I will first of all generate x star from my target distribution. I can, right? Because proposal distribution, because proposal distribution is for sampling. Next, as I said, we decided that we will generate uniform sample from uniform in 0, m q x star. That's what we did next, right? Clear? Then what will you do? If u is less than or equal to pi star of x star, right? What does it mean if u is less than pi star of x star? It means it is in this hashed area or this dotted area. Then what do? Accept, because this third condition, if condition, means that the sample you are generating is less than this. That means you should accept. So then accept x star. Else, what will you do? If it is greater than, you should reject and go back to step 1, and you can continue this until you get enough number of samples. And this thing can be continued until and unless you are getting adequate number of samples. Clear? But now this is not a common algorithm, or this is not a common way of implementing rejection sampling. In books you will not get this algorithm. In book the algorithm you will get is of slightly different form. So let me write that also. I should have written a little bit towards the left side, but let's see. Okay, the book version I am writing now. And both are essentially same, but this is more intuitive. Okay. The book version is simple. You will sample x star from qx and you will sample u from uniform 0, 1. Okay. And then you will check if u is less than equal to pi star x star divided by m q x star, then accept x star with probability pi star by m q x star, else reject. Okay. Now, can you tell me why these two algorithms will give you same results? Or do you think they will not? I am claiming that these two algorithms, left and right, red and violet, should give you same result. So, can you tell me why? It's very simple actually. See, whatever I was sampling from, I have scaled it. Okay, I have done that. Now, out of this, why do you think the second one is more popular? I said the first one is more intuitive because that's what we discussed. That was, but the second one I just now said is more popular. Can you give me a potential reason? That's not a problem. But it's very u0 to 1. That is the actual thing. But why is it more popular? Think about it. The second line is not dependent on the first line. You can do the first two lines parallelly. In the other case, you see, first you have to sample x star and then only you can sample u. You cannot parallelize the first two lines. In the second case, the first two lines are parallelizable. You can do sample separate, parallelly. And as a result, because you can sample parallelly, u is not dependent on x star now. It is more popular because at least little bit of parallelization you can get. Anyway, samplings are embarrassingly parallelizable. Okay. Any question on this? Otherwise, this portion is actually done. I have 10 minutes to prove that this actually works. Okay. Correct. Because think about it, x star can come 10 times. How many times will you accept it? What is the probability of getting x star accepted? It is that ratio. That ratio I did not write on the left hand one because it's still that probability only. Because the probability does not change. Even in that case, it is x star with that probability. And that probability comes from pi x. See, I multiplied that with n, right? So that is the probability. So I already showed it. So that means if you generate x star n number of times, only that is the probability with which it will be accepted. Okay, so that's what it means. Okay. Samples of pi star. Pi, or how is it pi also? I'm coming to that. But remember that sample of pi star is equal to sample of pi because every sample will be scaled by a constant number. So even intuitively you know that you can only sample from a distribution. Now whether you are sampling from pi or pi star should not matter because each sample is scaled. Is the probability changing? Think about this PDF. If this was an unnormalized PDF, right? If it is a normalized PDF, do you think that this shape will change? It will just be scaled every point. So if it is scaled, let's say it is reducing by a factor, then your m will reduce by that factor to make the envelope and everything remains same. But I will prove it also mathematically that it does work. Okay. But even intuitively it is very simple. If it is getting scaled, suppose it is increasing, then your envelope m will increase because the top has to be enveloped. And then we are using it. Without using it, what is this if condition? Why are you not using it to sample? You cannot sample from unnormalized distribution directly. Because you cannot. Can you sample from unnormalized distribution? How will you sample? For sampling from any distribution, you have to use fx inverse. That's what we did last time. Fx inverse you do not know for unnormalized. You cannot. It's not that we are not. If we can, we will happily do that. It's that we cannot. Okay. Okay. So now let me come back to this and ask one question. So I use uniform. Now suppose along with that, um, instead of uniform, if I had used Gaussian, okay, a Gaussian where the peak matches, okay, which out of this uniform and Gaussian do you think is a better proposal and why? You know the distribution of Gaussian? Let me draw it also. I was not willing to draw it because it will kind of mess up this figure, but let's see. So let's say I have a Gaussian, which is more like, I don't know, this. This, right? This can be a possible Gaussian. And you can obviously scale it. This is before scaling. And you can scale it and increase it. Okay. So out of these two, the one that I drew now and the green one, which do you think is a better proposal and why? Gaussian. How many things Gaussian? 1, 2, 3, many. How many things uniform? 1, 2, 3. Okay. Those who think uniform, why uniform? Let's start with that. Or it is just intuition. Okay. And those who think Gaussian, why Gaussian? Because I said earlier that Gaussian is a default one. Hmm? Yeah. Actually, that is not the reason. The reason is very simple. Think about with this, your acceptance probability will increase for many of the samples. So Gaussian is better for this because let us take the same x1 point. If I sample from Gaussian, it will be accepted more number of times as opposed to when I sample from uniform because that ratio m q star by pi star will increase. That means the acceptance ratio, the number of times samples are getting accepted on an average will increase. So that means if I have to sample 1000 samples, with the uniform I might need to actually generate 10,000 and only 10% is getting accepted. Whereas with Gaussian I might need to generate 2000 and 1000 will get accepted.
Yes, number Gaussian.
No. The number of accepted sample is still I'm keeping 1000. Really? Ah. Gaussian you may get 70 selected. So that selection ratio will increase. But ultimately when you are representing that number has to be same. So that means if the selection ratio increase, what does it mean? If my selection or acceptance ratio is let's say 50%, that means for every 2, 1 will be accepted. So if I need 1000 samples, I will generate 2000 because 1000 will be rejected, right? And that will be the case with let's say Gaussian. Now if my acceptance ratio is 10%, which is probably the case with uniform, then to generate 1000 samples that I can use, how many samples I have to actually sample? 10,000 samples. Okay, so from uniform I have to generate 10,000, but effectively I will get 1000. So the sample number of samples will increase. So that's why getting a good proposal is very important. Okay, and the more it resembles the original one, the better. For example, you know that in this case both are increasing and then reducing, both are symmetric, so it is resembling. So as a result, I mean, if you sample from the original one, the red one, if pi star is your proposal, what will happen? 100% acceptance. That's the best case, right? You cannot have more than 100% acceptance. Clear? No, peak that way will increase. Like the original one was the green one, right? So what I've drawn is the equivalent of green. Now I will multiply it by m and make it peak and match that. So from the green I went to the, so from this green I multiplied by m and got the envelope. So even from this I will multiply by another m, that will be m1, and I will get it this another envelope which will look something like this. So that won't happen because I have to anyways create the envelope, otherwise I am doing wrong. Clear? So okay, the question is why does it work? So how do we know that samples generated from rejection sampling are from pi of x. That's what we need to prove, right? Mathematically. That okay, intuitively we can understand that it is following the ratio, so it should be, but can we show it mathematically? So if I have to prove this, what do I actually need to prove? Like last time, I need to prove that given a sample x is accepted, it should follow the CDF of pi x. So like similar lecture, it will suffice to prove that probability of y less than equal to x given y is accepted is equal to integration minus infinite to x pi x dx. Make sense? The left hand side is basically saying the probability of the samples you are getting from the rejection sampling, and you need to prove that that comes from this CDF or this PDF. Correct? This is what you need to prove. How to prove it? What law will I use? What law will I use? There is a conditional distribution I can see. Product law, sum law. Okay. So first I will use the product law. So what is this equal to? This is equal to y. How can I write it? Probability y less than equal to x and y is accepted. Joint distribution divided by the marginal, I mean the conditional one. Or this is equal to probability of y less than equal to x and y is accepted divided by probability y accepted. Right? Let us try the denominator. Simple, right? Probability of AB by probability of B. Probability of A given B equal to. What is probability of y getting accepted? And this has to be the total probability. So probability over everything. Okay. This is equal to integration. First you will sample y. You will sample y from where? Q. You will sample y from Q of y. And given that you have sampled it, you want probability that that sample is accepted. You want probability of accept given y. And this is to be done for all y. Right? And the integration limit is because all y. Right? What is the probability? Probability of accept given y. Pi star by mqy. This is equal to integration minus infinite to infinite qy, and this we have already discussed. This is pi star y m qy cancels out dy. This is equal to 1 by m integration minus infinite to infinite pi star y dy. Clear? Simple? Nothing trivial. You first sample it and then you accept it and then you integrate over all possibilities. What do you think will be the numerator? Probability y less than equal to x and y accepted. What will be this equal to? This is equal to integration. First you will sample y from Q of y. Same thing. Sample y from Q of y. Then it is getting accepted again. Pi star y by mqy. But you are only looking at the probability not over all possible y's. You are looking for probabilities only for y that is less than equal to x. So what should change? What should be the limit? Minus infinite to x. That's what I am looking for. Clear? Previously I was looking at all possible y. So minus infinite to infinite. Now I am looking at only those y which is minus infinite to x. That's why the limit will change. dy is there. Cancels out. 1 by m integration minus infinite to infinite. No, minus infinite to x pi star y dy. So now what is the ratio? So what is probability y less than equal to x given y accept? Let's call it equation 1. This is my equation 1. This is my equation 2. This is my equation 3. So I will substitute 3 and 2 into 1 and do the ratio. What will I get? 1 by m and 1 by m will cancel out. Clear? And what is remaining? Integration minus infinite to x pi star y dy divided by integration minus infinite to infinite pi star y dy. 1 by n and 1 by m has cancelled out, I am not writing. What is the denominator? That is the normalizing constant. Right? Right? That is the thing that with which you divide.
1 upon.
I will write z in that sense. So that means what is this total thing? This is equal to integration minus infinite to x. I don't need to now write pi star, it is pi of y dy, which is equal to what we wanted to prove, right? So nothing equal to, let's try to prove. So this is your normalizing constant. So clear, what we are thinking from intuition can also be proved mathematically. Okay. Clear? So we'll stop here. But there is one problem with accept reject sampling, which is that many samples might get rejected. So ideally we will want to reduce that, and that's why we'll talk about a scheme where 100% samples will be accepted next time. So on Monday we'll start talk about important sampling, where everything is accepted. There is nothing rejection as such. Okay. Thank you.